Fun little exercise. Use the series expansion that you know of the Bessel functions to prove that this limit is equal to 1/2. So pause the video and have fun. We know what the Bessel functions are in terms of a series expansion. So we know that the Bessel function j1 of x, that you can write that as a sum of a summation index s going from 0 to infinity of -1 to the power s factorial, and then n plus s factorial, with n being the order. So in this case, it becomes 1 plus s factorial. And then we have x over 2 raised to the power of n plus 2s. So n, that becomes 1 plus 2s. Okay, so far so good, but we're interested in j1x divided by x. So that's just going to become sum s0 to infinity, copy paste, s factorial 1 plus s factorial. And then we have x to the power of 2s divided by 2 to the power of 1 plus 2s. Don't forget that nothing changes here in the exponent of the 2. We only divide by x. Okay, so we have a series expansion here. Let's write down a couple of terms, and let's start with the term s equal to 0. This becomes -1 to the power of 0. 0 factorial, which by definition or by extension rather, is actually also 1. And then we have 1 factorial. And then finally, we have 1 over 2 to the power of 1. So this first term actually is 1/2, which looks familiar. Let's have a look at the second term. Well, we have a rather complicated prefactor, but the important thing is that it's a coefficient of x squared, and then we have a coefficient of x fourth, and so on and so forth. So if we take the limit of x going towards 0, all of these higher terms will just vanish into oblivion, and the only term that's left is 1/2. So it's pretty easy to show that this limit indeed is 1/2.